Hello, once again. So this time I was presented with a problem on trees, specifically to demonstrate that on any tree with at least two vertices, that there are at least two vertices of degree 1. So how can we go about this proof? Well, let's see some of the ideas that we're going to incorporate into the demonstration. Recall that the number of vertices and the number of edges in a tree are strictly related. In other words, if this denotes the number of vertices, then it differs just by 1 in the number of edges. Well, with this in mind, we're going to introduce a few things. And along with the handshake lemma, we are going to develop our demonstration. So, what is that we have here? Where, let n be the number of vertices. Now we have that n is greater or equal than 2 by the assumption that we have here, right? So I'm going to denote bi as the degree of vertex I, where I ranges in the set from 1, 2, 3 up to n. So is all that I'm doing here is relabeling the vertices of T using the numbers from 1 to n. Right? So remember the handshake lemma. By the handshake lemma, we have the following: the sum of all the degrees, right, among the vertices is twice the number of edges. But, well, how do we establish this under this context? Well, this says that if I add the degrees ranging from 1 up to n, this sum is the same as 2 times, well, the number of vertices minus 1, right? Establishing this or based on this relation. But from here, I'm going to just rewrite a few things. And instead of writing this as a sum, I'm going to write it as d1 plus d2 plus d3 plus blah, 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 plus dn equal, right? This has to be n, this has to be 2. So this is really 2n minus 2. Now, look at the equation that we have here. Since this is a connected graph, being a tree, we must have that d is greater or equal than 1 for each I. And the reason why I just explained, well, this is a connected graph. T is connected. Right? That would be the reason. But this says that, look, the equation that I have here might be replaced by another one. So I'm going to make a change of coordinates. In other words, I'm going to just change these d's for something else that will make it a little bit more manageable. So instead of having this, I'm going to replace each di with the following. In other words, something along these lines. And you may say, what would be the use of this? Well, the thing is that now this xi, each of them are going to be greater or equal to 0, where xi is a non-negative integer. And it's just a change, right? A change of variables. But now, in the context of this, we now obtain this. Then, well, x1 plus 1 plus x2 plus 1 plus blah, 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 plus xn plus 1 is equal to 2n minus 2. But now, look, from this one, I obtained the following equivalent equation. This says that x1 plus x2 plus blah, 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 plus xn is equal. Look, I have n terms in this sum. Each of them have a 1. So at the end, the sum is n. So I'll subtract them, and I'll get the following, n minus 2. So now we can think of this as a distribution problem. Where we have n different entities to which we have to assign, well, n minus 2 identical objects. But, well, look, the only possible way to perform this task is if at least 2 of these xi's is 0. Is only possible if at least 2 xi's are 0. Why? Well, otherwise we wouldn't be able to come up with this particular equality, right? It's this 2 that is in front of us that is doing our work. So, conclusion. Therefore, well, at least 2 di's are 1. But what are the di's? The di's are the degrees of vertices. Well, thus, at least 2 vertices have degree 1. And well, this concludes our proof. Hope that you enjoyed. Take care.